My name is Daniel Hakimi bin Fauzai for group 5 and 6 for the case study, the design, fabrication and evaluation of 3D printing, GHNTS, GMGO, Viscary, PLLA, composite scaffold with the honeycomb microstructure for the bone tissue engineering. For group member, Daniel Hakimi, is me, Muhammad Nazran Adli, Wan Farahiyah Ifah, Muhammad Sofi, Nur Sadidatu Maisara, Khairi Naim, Umi Natra, Nurul Ashikin, Nur Alia Syakira, Nur Nadia, Aiminur Hakim. For introduction, the manufacturing technology is used in biomedical. The field is quiet device. The 3D printing technology has been designed to aid in the healing of autologous bone tissue. The widespread use of poly-1-latex PLLA material in the field of bone tissue repair. MGO PLLA bone tissue repair scaffold enhanced by introducing function filler into the PLLA matrix. The scaffold requirement with high porosity and interconnected pore structure, formation of the honeycomb structure in scaffold. For 3D printing based on the composite porous scaffold of the honeycomb structure.
For the method 2.1, material and reagent, general PLLA, L-lactite, stannous octoate, raw HNT, MgC12-6H2OAR, Na2C03, 10H2OAR, mouse embryo osteoblast precursor MC3T3, E1 cell, ALP and BCA, protein easy kit. For 2.2 is preparation of graph MGOS and graph HNTS. The picture below show the graph flow, and this is the graph flow. And then for 2.3, preparation of 3D printing composite ensemble. The GMGOS, GHNTS and PLLA particle were dry and mixed according to the formulation shown in table 1. And then the mixture was put into a twin screw extruded for blending and extruding. Third, the material were dry at 60 degrees Celsius for 12 H in blast dryer. And last, the dryer particle were thrown in a single screw extruded to produce ternary composite. 2.4, design and fabrication of scaffold. Scaffold were designed using a computer-aided design (CAD) software Unigraphic NX 12.0 and export as a rapid prototyping format. 2.5, characterization. First, transmission electron microscopy (TEM) to obtain the image of the MGOS and HNTS before and after surface grafting, as well as the section of the ternary composite scaffold. Second, Fourier transformation infrared (FTIR) to analyze FTIR spectra of the MGOS and HNTS before and after surface grafting. Third, thermographimetric analysis (TGA) to determine a material's thermal stability and its fraction of volatile component. Next, polarized optical microscopy to analyze the crystalline morphology of PLLA, GNTS, GMOS and GNTS PLLA ensemble. And then X-ray diffraction (XRD) to to observe the crystalline structure of the digital ensemble. Next, universal mechanical testing machine to observe the compressive and tensile properties of the 3D printing pure PLLA and ternary composite scaffold. Next, Abacus CAE 640 to determine the finite element analysis of stress construction around micro crack. And last, goniometer to determine water contact angle WCA of neat PLLA and PLLA scaffold. 2.6 Cell toxicity, proliferation and morphology. MC3T3E1 cell were seeded into triplicate at a density of 1x stand for cell per well for different period. After culturing for 1, 4 and 7 days, the cytotoxicity of the scaffold was assessed by leaf and DES assay for animal cell kit and observed by an inverted fluorescein microscope. Next, the MC3T3E1 cell were proliferated for 1, 4 and 7 days, at which time incubate in the solution of 10 ml of complete medium with 1 ml of CCK negative egg reagent for 3H. And last, the cell viability was reflected by tetrazolium monosodium salt assay. And lastly is 2.7 osteogenic activity. The ALP and BCA protein assay kit were used to evaluate the ability of osteogenic differentiation of MC3T3E1 cell on various scaffold. Next, the measurement of OD value was performed at 492 and 570 nm respectively. And then the ALP staining was performed by the CAKP kit under the stereo microscope. Next, MC3T3E1 cell were collected on the surface of scaffold in osteogenic induction medium to investigate the osteogenic induction effect of various filters on the scaffold for 21 days. Next, the stained cell were observed with 10% CPC in PBS or measure the quantity of calcium deposition with enzyme link immunos band assay plate reader at 540 nm. And lastly, all result staining were observed under a stereo microscope. That's all from me. Thank you.
3.1 Characterizations of GMGOS and GHNTS. The FTIR spectra were taken to prove the successful grafting on the surfaces of whiskers and nanotubes. Thermal decompositions of PLLA short chains was revealed at the stage of 200 to 350 Celsius, which is similar to the MGOS and HNTS in a previous study. Heat decomposition behavior of sample has been analyzed by TG method to further obtain the amount of surface grafted POIIA chains on the surface of MGO and HN samples. The crystalline and thermal properties of materials prepared by mixing and extrusion technology were acquired, which could guide the process of subsequent 3D printing. No matter which type of filler was added, the crystalline rate of the composite consumables would be higher than that of neat PLLA. For 1% GHNTS, 1% GMGOS, PLLA ternary composite consumables, a number of small spherulites appeared at 8 minutes, which could be attributed to synergistic effect of micron and nanofillers in PLLA matrix. The onset and maximum decomposition temperature of all composites decrease compared with those of pure PIIA, especially for the 2% GMGOS PLL composite consumable. The values of onset reduced to 230 Celsius and 280 Celsius, which are much lower than those of NITS PIIAS. 3.3 Physicochemical properties of the 3D printed composite scaffold. 3.3.1 Fabrication and design. The model and microtopology structure of the 3D printed composite scaffolds for in vitro biological evolution were exhibited. Scaffold possess a combination of large and small honeycombs, and such pore size and porosity were mainly based on the consideration of cell proliferation and migration.
Composition scaffold had a remarkable increase in yield strength in comparison with the net PLA scaffold. Yield strength and compressive moduli of the composite scaffold will be greatly enhanced by the addition of DMGOS and DHNT at a stable ratio. Matrix scaffold to contain DMGOS has superior cell proliferation ability compared to PLLA scaffold and scaffold A. MC3T3E1 cell on the scaffold B exhibited a low willingness to proliferate. Many cells will also emerge inside the scaffold, demonstrate the stereoscopic growth and proliferation of cells. The sporadic behavior of MC3T3E1 cell on the different scaffold was also studied via LSCM. Cells on all scaffolds show enhanced pseudopodia and spreading area. According to Ridley studies, the cell migration process was greatly regulated. CDC42 and RHO family proteins. Osteogenic activity of the 3D printed scaffold was considered in terms of LALP activity and calcium disposition in vitro. ALP expression on the composite scaffold containing GMGOS such as scaffold B and C exhibited a significant difference from that of pure PLLA scaffold.
In this study, a kind of new 3D printing consumable containing PLLA matrix, GMGOS and GHNTS were designed. Moreover, GHNTS per GMGOS per PLLA composite scaffolds with the large and small honeycomb in a pore size of 510 plus minus 20 micrometer and 210 plus minus 15 micrometer were further successfully fabricated via 3D printing. That GMGOS and GHNTS can be used to improve the mechanical properties of composite scaffolds, including tensile and compressive properties, and promote cells adhesions, migration, proliferation, and osteogenic differentiation on the scaffolds. The GHNTS per GMGOS per PLLA composite scaffolds owns good mechanical properties. Cell affinity and osteogenic activity would be a promising candidate as a bone repair materials.